All right, so what we're going to do today, again, we're just continuing on with exponential equations, combining what we just did this morning with what we did the other day. All right, so looking at an example. So my first example, there's no way I can write it out. This big, long sentence there, I can't write that out, but here's example one. A town with a population of 80,000 has been growing at an average rate of 4% for the last 15 years. Assume this growth rate continues in the future. The function that models the town's population growth is P equals, so here we'll write down example one. P equals, that's our population, 80 times 1.04 to the power of n, where our P of n, or I just wrote P, depends on function notation or not, represents the population in thousands, and n is the number of years from now. All right. So we want to determine the number of years from now it would take for the town population to reach 100,000. All right. Now, the first thing is that you can see this is exponential growth, right? We have our A value with a starting amount because population is measured in thousands. So starting population is 80 or 80,000. You can see it's an exponential growth function because our value inside here, our B value, is greater than 1. And we are looking for n, how long it will take. And the question is saying, when is the population going to expect it to be 100,000? Well, that means because this function is talking about the population in terms of thousands, we're looking at a p-value of 100. And so I'm going to substitute in that p-value. So I have 100 is equal to 80 times 1.04 to the power of n. All right, now we are going to solve for n. Guess what? That's an exponent, which we looked at. So you know what we're going to have to do is what we did earlier today, the log function. But we're not yet. We got one extra step here. And that extra step is getting rid of that 80. All right, so I'm going to divide both sides. Because it's attached, the only way I can do is divide it off by 80. All right, so those 80s divide out. I have 100 divided by 80. I'm using my calculator here. I'm getting 1.25 over here. And that is equal to our, well, I don't need the brackets anymore, 1.04 to the power of n. Now, this is very similar to what we did this morning. Now is when I'm going to take the log of both sides because, again, I want to solve for the exponent. All right, so I take the log of 1.25, which is obviously going to be a small number, and I take the log of my right side here, which is the log of 1.04 to the power of n. All right, now, in my calculator, I type in the log of 1.25, and I get 0.097. All right, but again, this is where I'm going to use that log rule, where I'm going to bring the n down to be a normal number. And so I'm left with n times the log of 1.04. All right, and once again, I keep it going here. I can find the log of 1.04, which is going to be a decimal for sure. Maybe negative, so I shouldn't jump the gun there. It's 0.017. All right, and then finally, the last step is to get n by itself. 0.017, divide both sides by that numerical coefficient. All right, so those divide each other out, and 0.097 divided by 0.017. And n is equal to 5.71. And again, because this is a word problem, got to take your answer, interpret it. I'm not just asking you to solve for n, I'm asking you to tell me what that means. And what that means is, therefore, the population is expected to be 100,000, and I believe our n was in years, yes, in 5 0.71 years. There we go. All right, so again, taking what we had before, an exponential equation. This first step, though, a little bit extra. But again, we also have to sub in a number, which we didn't do earlier today, and we get our population. All right, let's try another one of those. Let's see here. All right, so example number 2, where we're looking at, let's see here, a house. Oh yes, real estate. Love real estate. So let's see here, example 2. A house was purchased for $450,000 in 2018, and the house's value has been increasing at an average rate of 8% per year, I should say. Assume this growth rate continues in the future. Determine the number of years from 2018 it would take for the house to be valued at $600,000. So in this question, I don't even have the equation yet. So I have to come up with it, then substitute my values in, and then solve it. All right, so I'm going to come up with my equation. So I'm going to call this value, I guess, the value of the house. All right, now, the starting value of this house, it says, is $450,000. So there's our A value. All right, there's the starting amount. It is increasing at a rate of 8%. And again, when we're looking at finding our B value, you have 100% of the value of this house plus another 8% for a total of 108% from year to year. Again, percentage useless in calculating in math. Got to convert it to a decimal, so I have to divide by 100%, and I get 1.08. That is my multiplying factor. All right, and I guess we'll call it, and again, number of years since 2018. That is just coming up with the equation. That's what we did the other day, developing the equation, coming up with it, and then substituting and solving. But this time, our value, we want to know, when is the house going to be worth $600,000? All right, so I'm going to substitute this V value into my equation. And so now what I have is I got 600,000 is equal to 450,000, which was the initial value of the house, times 1.08 to the power of n. All right. So again, now we're into a point where it looks similar to the last example. And so the first thing I can do is I have to get rid of this 450,000. It's attached. So the only way to do that is divide both sides by 450,000. All right, so they're gone. If I take 600,000 and I divide it by 450,000, I get 1.33. All right, but over on the other side, I still have my 1.08 to the power of 9. All right, now here's where, because we're going to solve for n, we're going to take the log of both sides. So I take the log of 1.33, and I take the log of 1.08 to the power of n. The log of 1.33 is a number. All right, and if I type that in, I'm getting 0.125. All right, again, I'm going to use my log rule. That's the whole point of why I use the logs. I'm going to bring my n down in front. So then I have the log of 1.08. All right, now again, that's a number, so I'm going to solve for that number. Let's see here. The log of 1.08, going to be a small number again. I'm getting 0.033. Okay, and now the final step again, dividing by my numerical coefficient here to get that n by itself. So I'm going to divide by 0.033. Do that to the other side. And let's see here. So those are gone. Those divide each other out. My n is going to be, let's see, 0.125 divided by 0.033. I divide those two and I get 3.79 years. And so therefore, the house has a value of 600,000, 600Ks, 3.79 years after 2018. There we go. So that one we actually had to come up with the equation first, substitute in a value, and then solve for our exponent. All right, stepping it up. So let's on to example number 3, where we start to deal with our half-life formula that we had there the other day. Let's see here. All right, so this is a specific type of exponential, in this case, decay. All right, so this is a true example here. So this is example number 3. Always like to bring science and real life applications, financial and science stuff into math, because that's the more interesting stuff to me anyways. So example 3, after the accident at Chernobyl, I'm not sure if you know about that or not, the nuclear disaster in Russia, around 1986, I think, or 84, somewhere there. A radiation detector measured the radioactivity of cesium-137, which has a half-life of 30 years, unfortunately, to be 20,000 becquerels. All right, so that's the becquerels is a unit of measuring radiation. But so we start off at 20,000 becquerels, which would not be good for you. If a safe amount of radiation is to return is roughly 155 becquerels, how many years will it be before the people of Chernobyl can return to their homes? Now, again, this is talking about half-lives. And so we have our half-life formula, which is n is equal to n naught. Again, the multiplying factor is 0.5 because we're talking about half-lives. And our exponent is the time divided by the half-life. All right, so this is a specific exponential decay question. All right, now, again, the n is your final amount. N naught is your starting amount. T is how much time has gone by, and H is the half-life. Now, to go and return to Chernobyl, a safe amount is 155 becquerels. That's what you need to finish at to return to this city. All right, now, N naught is the starting amount. And right after this accident, there was 20,000 becquerels of radiation. Not good. This city was, I believe, the size of Oshawa, if that helps out. The time elapsed. How much time has got to go by before it is safe? We don't know that. But we do know the half-life of cesium, which was leaked into the atmosphere and into the city, is 30 years. So it just takes 30 years to go from 20,000 becquerels down to 10,000 becquerels. All right, not good. Now, I'm going to substitute those values in. All right, so I've got 155 here. 155 here. So that's our final amount. And not our initial amount of radiation that's in the city is 20,000. Again, special exponential decay, so our multiplying factor is 0.5 because we're talking about half-lives. Our time, I don't know. And our age, I do know, it's 30. All right, so again, we're solving for t. It's an exponent. Now, our exponent here is a fraction, so that's going to change things up a little bit, even a little tougher. But before we even do that, I have to get rid of this 20,000. All right, so I'm going to divide both sides by 20,000. And so those divide each other out. They're gone. And wow, I take 155 and I divide it by 20,000. I'm going to go to the first two non-zero numbers here. 0.0078, really small. Now over on this other side, I have 0.5 to the power of t over 30. All right, now I got to solve for that exponent. I'm going to take the log of both sides. All right, so I'm going to take the log of 0.0078. I'm going to take the log, like I said, of 0.5, and that exponent is t divided by 30. All right, now the log of 0.0078, that is so small, that might even be negative. And it is. It is negative 2.11. All right, now, again, here's where people get messed up here. I'm going to apply the log rule. I have a numerator and a denominator. So when I bring that fraction or bring that exponent, which is a fraction, down to be a normal number, I'm going to write it as such. So I have t as my numerator, 30 down below is my denominator. All right, and that is going to be times the log of 0.5. All right, now, again, I can simplify for this log of 0.5 just by typing it into my calculator. So I have negative 2.11 here, t divided by 30, and then the log of 0.5, I believe, is negative 0.301. Now, this is where a lot of students get stuck. All right, how do I solve for t, right? Here's what I'm doing. I'm just going to put these two numbers together. I have a numerator and a denominator, so all that means is it's a divided by question. It's not done yet. So I'm going to take that negative 0.301 and divide it by 30. All right, so running out a bit of room here. Oops. Go up here. I have my negative 2.11. All right, I still have my t here. Now I take negative 0.301 divided by 30. It's going to get even smaller. And in fact, it is negative 0.01. All right, and so now I'm going to divide by my numerical coefficient to get t by itself. So I divide by negative 0.01. Do that to both sides. And my t value, I take negative 2.11 divided by negative 0.01, and I end up with 211. Now, I mentioned this before the other day, when you're dealing with the half-life and doubling times formula, t and h have to be in the same units because they're dividing each other. Our half-life is in 30 years. That means our t is in 30 years. And so in this city, it's going to take 211 years before people can return to that city safely. If that happened in 1984, there's still more than 160, 170 years left before they can go back. The city's useless. If you're interested in that, check it out on YouTube. It's quite interesting stuff. You can go there now, but not for very long. You get a 5-minute window or something, because the radiation is still bad. All right, last example. That was a half-life formula. Now it's time to do a little doubling times. It's going the other way. Hopefully a nice, happier situation. All right, the old world population again. All right, so it's terrible. Example 4. There we go. All right, so it's all about the world's population. Again, the world population, it's changing, so that's why it's a little bit different than the last the other day. But in this question, it says the world's doubling time, or the world population is doubling every 35 years. In 1980, the total world population was about 4.5 billion. If the doubling period remains at 35, find the year in which the world population will be 36 billion people. I think we're around 8 or 9 right now, somewhere in there. It's something you can Google very easily. When are we going to be 36 billion people? 4 times the amount of people that we already have on Earth. All right, so again, this is a doubling time formula. All right, so that's a specific exponential growth. So we have n equals n naught and times 2, because our multiplying factor, we're doubling. And this time it is t over d is our exponent. All right, now if I again read the question here, its doubling time is 35 years. We got that. How much time? We don't know yet. So put a little question mark there. Now in this question, it says in 1980. So that's our n naught. That's our starting point for this question. Is 4.5. I'm going to put a B there for billion. And I want to know, when are we going to reach 36 billion people on Earth? Crowded. All right. So here we go. I'm going to substitute my values in. And so I've got n here, which is 36 billion, divided by, well, we got n naught here, which is 4.5 billion. All right, again, I have my T2 there. And again, T, I don't know. I don't know how long that's going to take. But D, the doubling time is currently 35 years. There we go. All right, so there it is. I've got my equation, got my information here, plugged it in. That alone is not easy. Now I'm going to divide, to solve for T here, just like I did before. I'm going to divide by 4.5 billion. On both sides. So those 4.5 billions divide each other out. Now I got 36 billion divided by 4.5 billion. And I end up with, oh, a nice number here. 8. All right, is equal to 2t to the power of 35. All right, now again, this is where we're solving for the exponent. And all we have is our power there. So I'm going to take a log of both sides. All right, now the log of 8, again, that's a number I can figure out by just typing it in my calculator here, and the log of 8 is 0.9. Again, this is where I'm going to use my log rule. I'm going to bring my exponent down front. It's a fraction, so I'm going to write it as such. My numerator is t, my denominator is 35, and I'm going to multiply that by log of 2. All right, again, further simplify. I have 0.9 here. I'm going to figure out the log of 2. It's going to be a decimal because that's already a small number there. So the log of 2 is 0.3. Again, this is where I always find students get stuck. Can't solve for t at this point. I'm just going to put these two numbers together by dividing them, taking 0.3 and dividing it by 35. And so I've got 0.9 is equal to t. All right, I take those two numbers and I divide them. What am I going to get here? So I divide them, I get 0.0. How many zeros did I get there? 0 again, 9. All right, and then finally, getting t by itself, we divide each side by 0.009. So those divide each other out. All right, and so t is going to be whatever, 0.9 divided by 0.009. And I'm getting 100 years. Now the question, again, this is a word problem, so I got to interpret my answer here. It says, find the year in which the world population was 36 billion. Our starting point of 4.5 billion was in 1980. And so, therefore, the population of the world will hit 36 billion people in the year, let's see, we started off in 1980. That was our initial value. 100 years from that, that's what our answer said. 100 years will have gone by. And so in the year 2080, right now, we could project that there will be 36 billion people on the earth, which again, I believe is 4 times what we have now. I believe we're at 8 or 9 billion people now.